Control valves. Definition, types, and working principle. Introduction. In industrial process control systems, the control valve plays a crucial role as the final element responsible for directly controlling the process variable. It is the mechanical device that physically regulates the flow of fluid, whether it be liquid, gas, or steam, within a pipeline or system. Control valves receive control signals, typically pneumatic or electrical, from a controller and convert those signals into movement that changes the valve's opening, thereby adjusting flow rate, pressure, or temperature to maintain a desired set point. The control valve is therefore the heart of any control loop. Without it, the automation system would have no physical means to execute the control commands calculated by the controller. Basic concept of a control valve. A control valve is a power-operated device that modifies the flow of a process fluid. Its main purpose is to control parameters such as flow rate, pressure, temperature, or level in a process system. It achieves this by varying the size of the flow passage as directed by a signal from a controller. The typical control system loop looks like this. Sensor, transmitter, measures the process variable, e.g., temperature, pressure. Controller, compares the measured value with the set point and sends a corrective output. Control valve, acts upon the process fluid to bring the variable back to set point. In simple terms, a control valve receives a signal and moves in response to regulate flow through the system. Main components of a control valve. A control valve consists of several mechanical and pneumatic or electrical parts that work together to perform accurate flow regulation. 1. Valve body. The valve body is the primary pressure-containing structure that holds the internal parts of the valve and connects to the pipeline via flanges or threaded ends. It determines the valve's capacity, pressure rating, and type of flow pattern, straight, angle, etc. Common materials: stainless steel, carbon steel, cast iron, or bronze. 2. Trim. The term, trim, refers to the internal components that come in contact with the fluid, such as the plug, seat, and stem. The trim design determines how the valve throttles the fluid. Plug, disc, the movable part that controls flow. Seat, the stationary surface where the plug rests to stop flow. Stem, connects the plug to the actuator. 3. Actuator. The actuator provides the necessary force to move the valve stem and plug. It receives a signal from the controller and converts it into mechanical motion. There are 3 main actuator types: pneumatic, air-operated; electric, motor-driven; hydraulic, oil pressure. 4. Positioner. A positioner ensures the valve opens precisely according to the control signal. It receives both the input signal and the valve stem position feedback, adjusting air pressure to maintain accuracy. Example: for a 50% control signal, 12 mA, the positioner ensures the valve is 50% open, even against friction or fluid forces. 5. Bonnet. The bonnet is the cover that contains the packing gland and provides a seal to prevent fluid leakage along the stem. 6. Packing. Packing materials, Teflon, graphite, etc., are used around the stem to prevent leakage of process fluid from the bonnet. Working principle of a control valve. The operation of a control valve can be understood as the interaction between the signal, actuator, and valve body. Step-by-step explanation. The controller monitors a process variable, for example, pressure. If the process deviates from the set point, the controller sends an output signal, usually 4 to 20 mA, to the IP current to pressure converter. The IP converter changes the electrical signal into a proportional pneumatic pressure, usually 3 to 15 psi. The pneumatic signal is sent to the actuator, which converts this pressure into motion. The actuator moves the stem, changing the valve plug position, opening or closing. This alters the flow rate through the valve, which in turn changes the process variable back toward the desired set point. This feedback mechanism ensures stable control of process conditions such as temperature. Flow, types of control valves based on body design. Control valves are available in several designs depending on the process requirements. 1. Globe valve. Description. The most common type. The flow passes through a seat and is throttled by the movement of a plug in a linear motion. Advantages. Precise control, good for throttling applications. Applications. Flow and pressure control in chemical and oil industries. 2. Ball valve. Description. Contains a rotating ball with a hole through its center. Rotation of the ball changes the flow passage. Advantages: tight shutoff, low torque, quick operation. Applications: on-off control and some modulating control of liquids and gases. 3. Butterfly valve. Description: features a disc mounted on a rotating shaft. The disc rotates 90 degrees to open or close the flow. Advantages: lightweight, low cost, suitable for large pipe diameters. Applications: cooling water, air, gas services. 4. Plug valve. Description: uses a tapered or cylindrical plug with a port through it. Advantages: quick acting, low maintenance. Applications: gas, slurry, or corrosive fluids. 5. Diaphragm valve. Description: uses a flexible diaphragm that presses against a seat to control flow. Advantages: leak tight, ideal for corrosive fluids. Applications: chemical, pharmaceutical, and food processing. 6. Gate valve. Description: primarily used for isolation rather than control. Advantages: minimum pressure drop when fully open. Applications: on-off service in pipelines. High voltage types of control valves based on actuator type. Type: power source. Features: applications: pneumatic actuated valve, compressed air, 315 psi. Fast response, widely used in industries. Electric actuated valve, electric motor. Precise, used where air is unavailable. Hydraulic actuated valve, hydraulic oil pressure. High torque, used in heavy-duty applications. Upward trend flow characteristics of control valves. The relationship between valve opening, travel, and flow rate defines the valve's flow characteristic. Common types: linear. Flow rate changes directly with stem travel. Used in level control applications. Equal percentage. Each increment of stem movement changes flow by a constant percentage of the previous flow. Ideal for pressure or temperature control. Quick opening. Large increase in flow for small stem movement. Used in on-off services. Control valve flow equation. The flow capacity of a control valve is expressed in terms of the flow coefficient CV, where equals flow rate gallons per minute equals valve flow coefficient equals pressure drop across valve psi equals specific gravity of fluid. This equation helps engineers select the correct valve size. Control action: air to open versus air to close. Control valves can be configured for fail-safe operation depending on process safety needs. Air to open, fail close, valve opens with increasing air pressure and closes on air failure. Air to close, fail open, valve closes with increasing air pressure and opens on air failure. The fail position, open or close, ensures safe process conditions in case of power or signal loss. Accessories used with control valves. To enhance control and reliability, various accessories are mounted on or near the control valve. IP converter, current to pressure, converts 4 to 20 mA signal to 3 to 15 psi. Positioner, ensures accurate valve positioning. Air filter regulator, maintains clean, stable air supply. Solenoid valve, provides remote on-off control for air supply. Limit switch, indicates valve position, open or closed. Handwheel, allows manual operation in emergencies. Materials of construction. Material selection depends on process conditions like pressure, temperature, and corrosion potential. Component. Common materials: body, carbon steel, stainless steel, bronze. Trim, stainless steel, hardened steel. Seat, PTFE, metal alloys. Packing, Teflon, graphite. The applications of control valves. Control valves are essential in virtually every industry that deals with fluids. Oil and gas, regulating crude oil, natural gas, and steam flow. Chemical processing, controlling reactant flow rates and temperatures. Power plants, steam pressure and boiler feedwater control. Water treatment, flow and level control in purification plants. Pharmaceuticals, accurate dosing of fluids and gases. Maintenance of control valves. Proper maintenance ensures reliability, safety, and accuracy. 1. Routine checks. Inspect actuator and positioner for leaks. Verify stem movement and calibration. Check packing tightness to prevent leakage. 2. Preventive maintenance. Clean air filters and lines. Replace worn packing or trim parts. Calibrate valve positioner regularly. 3. Troubleshooting. Symptom. Possible cause. Remedy. Valve not moving. Air supply failure. Check compressor and filters. Hysteresis, sluggish response. Sticky packing or faulty positioner. Lubricate or recalibrate. Leakage. Damaged seat or plug. Replace or lap seat. Hunting, oscillation. Oversized valve or tuning issue. Resize valve or retune controller. Control valve sizing and selection. When selecting a control valve, engineers consider maximum and minimum flow rates, pressure drop across the valve, type of fluid and its characteristics, required accuracy and response time, fail-safe position open or closed. Improper sizing can lead to poor control performance, excessive wear, noise, or cavitation. Cavitation and flashing. Cavitation occurs when liquid pressure drops below its vapor pressure, forming bubbles that collapse violently, causing noise, vibration, and erosion. Prevention. Use multi-stage or anti-cavitation trim. Avoid excessive pressure drop. Flashing happens when pressure remains below vapor pressure downstream, causing permanent vapor formation. Prevention. Use special valve designs or downstream diffusers. Example. Practical control valve in operation. Let's consider a steam pressure control system. The process requires maintaining steam pressure at 4 bars. A pressure transmitter senses pressure and sends a signal to the controller. The controller compares it to the set point. If pressure rises above 4 bars, the controller sends a signal to close the control valve slightly. If pressure drops, it opens the valve to allow more steam flow. This continuous adjustment keeps the system stable. Importance of control valves in automation. In modern industrial automation, the control valve acts as the interface between electronic control systems and the physical process. Even with advanced digital controllers and sensors, accurate process control is impossible without a well-functioning control valve. A properly sized, calibrated, and maintained valve ensures stable operation, energy efficiency, reduced downtime, improved product quality. Summary table. Parameter. Description. Device. Control valve. Function. Regulate flow, pressure, temperature, or level. Signal input. 4-20 mA electrical or 3-15 psi pneumatic. Main parts. Body, trim, actuator, positioner, bonnet. Types: body, globe, ball, butterfly, plug, diaphragm. Types: actuator, pneumatic, electric, hydraulic. Characteristics: linear, equal percentage, quick opening. Applications: oil, gas, power, chemical, water industries. Common issues: leakage, cavitation, hunting, air failure. Control action: air to open, air to close. Conclusion: a control valve is a vital component in process control systems, bridging the gap between control signals and actual physical change in the system. It allows precise manipulation of process parameters by adjusting the flow of fluids through pipelines. Understanding the types, working principles, and characteristics of control valves is essential for every instrumentation technician or engineer working in automation, oil and gas, power, or manufacturing industries. Proper selection, sizing, and maintenance of control valves ensure process efficiency, safety, and long-term reliability. In summary, while transmitters and controllers handle thinking in automation, control valves do the acting.